All right, now the recording looks correct. What I want to do today, so today is really going to be about Lenz's law. But before we get to Lenz's law, I just want to do another example of working with Faraday's law of electromagnetic induction. Again, dare I say that the actual calculations of Faraday's law of electromagnetic induction are fairly straightforward and easy. It's not a lot of complication. This one just becomes more complicated because our magnetic field has a function, right? But that doesn't mean that we aren't equal to it. We've seen worse calculus in this class. So let's just jump right in. Woo, come back here. We'll jump right in to what we've got here. So we know that the EMF is going to be equal to the change in magnetic flux in time. Again, I tend to do the version that's got the absolute value symbols around it so that I don't have extra minus signs floating around distracting me. But I've got to figure out, right, what my changing magnetic flux is going to be. Well, my magnetic flux is B times A times cosine theta. I ask myself the question, which of these is changing? There's three things there. Which one's changing? The field, right? It tells me right here that the field is changing according to this function. That function depends on time, doesn't it? So I know that when I stick this in here, my EMF is going to be the derivative with respect to time, because derivatives is nothing but ratios, of B times A cosine theta. We're going to call that equal to 1 because it tells me, right? The B field is oriented perpendicular to the plane of the coil. Wait a second, Mr. Balogh. If it's perpendicular, isn't the angle 90? What's the angle in this dot product? It's the angle between what two things? The field and the area. So if you have like a flat plane, right? And the magnetic field is perpendicular to this plane, which way is the magnetic field going? Straight up or down, right? We'll just say straight up. Okay? So here's the B field. They're saying that the coil, the plane of the coil is lying in that plane, right? That the plane is perpendicular to the magnetic field. What direction is the area vector? It's perpendicular to the plane of the area, right? So in fact, if a magnetic field is perpendicular to the plane that a coil is lying in, the angle between the area of that coil and the magnetic field is? No, it's 0 or 180. But in this case, it's 0. What's cosine of 0? 1. All right. So this is the EMF of N, right? dt of my field, which is AT squared plus C, times my area. It says radius R, so I'm going to assume it's a circle. So that would be pi R squared. All right. That's technically all inside the derivative right now. But can I pull stuff out? What can I pull out? Pi R squared, right? Because it's not changing in time. That's pi R squared N. And then what's the derivative of AT squared plus C? Plus nothing, right? And so I end up with just sorting some things around. 2 NT A. We usually put numbers in front followed by N and then sort of variables and then anything else. A pi R squared. So there it is, right? That's the EMF as a function of time. What's the EMF at time 0? 0. And as time goes on, right, it gets bigger and bigger and bigger, which makes sense because the magnetic field is getting bigger and bigger in time, right? So again, that's another way to have a change. The example that I did last time didn't have derivatives in it. It wasn't instantaneous because we had a time interval specified, right? But this example right here, if we know the function of how our magnetic field is changing, then we can find that instantaneous rate of change. And, you know, the miracles of a derivative, the miracles of a ratio. Let's show you. Oh, well, I don't show you this video because I brought the demo. I don't need this video. Okay, we'll show this one. This guy always looks nice and bored. Where is it? Oh, apparently there were problems with the video posted on YouTube. They gave me a copyright strike because of the music that I played. So I'm fixing that. A couple years ago, I could post those and they would never copyright strike me because I would always say that it was fair use. And now they've taken away all those guidelines. So. All right, here we go. Oh, this one we've got to turn the lights off because it's hard to see. Wow, that worked. Nope. Try again. Worst designs switches in the world. All right, here we go.
When a wire coil swings between the poles of a magnet, a voltage is generated in the coil. We'll use this coil connected to a small light bulb to show how that voltage changes as the speed of the moving coil is increased. If we swing the coil into the magnet slowly, the light bulb does not react.
Not at all. Slow-mo. Well, not really slow-mo. And nothing going on. This is not exciting. Are we changing the magnetic flux? Can they show me the picture again? Yeah, see, we're going through a magnet.
A slightly faster swing produces only a dim light,
which we can't see because the video is dumb. Do it higher. Do it higher. So it did light up just a little bit. Come on, be obvious. You can do it. Keep watching it. Keep watching it. Okay, slow-mo. All right.
A faster swing lights the bulb brightly.
Do you see it flashing up there? Yeah, right? He looks really interested, doesn't he? Slow-mo. Do the slow-mo. See it flashing? Lighting up brightly. You're going to do a variation of this experiment in lab, where you're going to swing a pendulum through a magnet, and we're going to measure on the computer the voltage that we see. And we're going to tie that into Faraday's law of electromagnetic induction. Okay. It has come. It has arrived. Nope. No, not that lens. Camera lens is LENS. All right. Oh. You guys won't be able to see a single thing I draw unless I do this. All right. Well, no, Lewis isn't onto something. Okay, so it is safe to say that this is the hard part of Faraday's law of electromagnetic induction. Let's review real quick. Electromagnetic induction teaches us that if we change the magnetic flux through a coil of wire, we will get a voltage and currents and everything else, right? We can make light bulbs light up, do whatever we want. Invent the universe as we know it. Lenz's law describes how a coil will react to that changing flux, specifically giving us a direction for the voltage and the current in those coils. And when I say the word direction, you should panic because that means what? Right-hand rules. And vectors, right? But we should back up just a little bit because we need to state, right, that this is a law. This is an observation about how the universe reacts to changes in magnetic flux. Faraday's law of electromagnetic induction gives us an idea of what the magnitude of those EMFs are. Lenz's law tells us not why, but what direction all these things are going to happen, and then importantly is going to lead us into the future here with our application. So what is it first of all? So I don't know, there's no good way to teach this. Maybe we should just jump in. Yeah, we're just going to jump in, whole hog. We're not even going to test the water. We're just jumping in, okay? So, no, we did test the depth of the water, and it's deep. Okay, there's a coil of wire. Not doing anything, just sitting there, right? Minding its own business. When all of a sudden, I bring a magnet close to this coil, what's going to happen to the change in magnetic flux? It's going to increase, right? It's going to get bigger. Lenz's law describes how the coil reacts to that change in magnetic flux and gives us a direction for the voltage and current in that coil. Lenz's law is a statement that says that a coil will always fight the change in magnetic flux through it. That's what Lenz's law says. It doesn't sound too bad, right? A coil of wire, when exposed to a changing magnetic flux, will do everything it can to fight that change, to slow down the rate of change of magnetic flux. What's the magnetic flux in the coil right now? It's 0. What does the coil want the flux to be? 0. And so if I change it and suddenly increase it, what's the coil going to say? No way, buddy, right? It's going to fight the change in magnetic flux. But what is it going to fight with? Yeah, all it has is charges. The coil can only create fields. It can't create anti-fields, right? There's no such thing as a negative anti-magnetic field. But the coil can create its own magnetic field. How is it going to do that? Last chapter, if you put a current in a coil, we can get directions for the magnetic field in that coil, right? Lenz's law tells us that a coil of wire will always fight the change in magnetic flux through it. If the flux is increasing, the coil will work to decrease that flux by generating a field that fights it. If the flux is decreasing, like it had magnetic flux and now it's being taken away, the coil will add field of its own to try and keep that magnetic flux going. A coil will always fight the change in magnetic flux through it. But that's only the tip of the iceberg. It'll always fight the change, and the change can be several things. Okay? So we're going to go from, say, like a before picture to an after picture. We'll stick it right there. Okay, so before we started, we had 0, and then let's just say that I'm taking a magnet such that its north pole of this magnet is oriented towards the screen. What direction will the magnetic field be pointed in the plane of the coil if the north pole of the magnet's towards the screen? If I take a magnet and I hold it up and I move it towards the screen with its north pole, south pole towards you, north pole towards the screen, which way will the magnetic field be pointed in the plane of the coil? In.
Oh wait, do you mean like North Pole, or do you mean like the North Pole?
I said North Pole. I didn't mean where Santa Claus lives. There's the coil. Here's my magnet, North Pole on this end, right? What actual North Pole? What do the magnetic field lines on the North Pole of a magnet do? They come out, right? So if I bring that North Pole close to this coil, which way are the field lines going? They're coming out of the magnet and passing into the plane of the coil, right? We good? No, but I'll shake my head. Okay. So, what happened to the flux? Did it increase or decrease? It increased. We started at 0, we got to something, didn't we? However, that flux has a direction, okay? And we've got to deal with that direction because it's safe to say, or maybe we can guess, that those are two different situations, aren't they? Both of those were increases, weren't they? Okay, it's just that what's going on in the second one? Which end of the magnet did I bring towards the screen? That would be the south pole, right? So the only difference between the two pictures that I've drawn here is the direction of the magnetic field to begin with, right? But both of these represent increasing flux, don't they? We're going from nothing and we're going to something, but that something can have direction. Okay? I can draw, same idea, upside down. And let's move that over here, because why not? And copy that right there. And I love electrons. Okay. There we go. What are these examples of? Decreasing flux, right? And just to be pedantic and clear and have everything, what would it look like for there no change in flux? The before and after picture would be identical, right? Either totally blank or with field in it, right? Okay, so we have these two regimes, these two ways that flux overall can change. Flux can increase, it can decrease, and then it can also stay the same, but what's the EMF going to be if the flux is constant? 0. Okay. So we're going to look just at the increasing and decreasing. Again, it's a before and after picture, right? Okay. But the reason I've drawn all these pictures is because the direction of the initial field does matter. Lenz's law says that it will fight the change. Okay? So let me give you a 3-step process to go through when you are asked to find the direction of induced voltage and current in a loop. Number 1. Determine how the flux is changing. Okay? Now, in this, you have to figure out, is it increasing or decreasing? and you need to be careful about the direction of the magnetic field. Those two things have to be identified, otherwise you're going to crash and burn really hard, okay? So you've managed to figure out increasing or decreasing, right? And the directions in my examples here, we can just kind of see them, right? But oftentimes you're being asked to figure out the direction of the magnetic field and whether that field is increasing or decreasing the flux through the coil. Those are two different ideas, right? Increasing and decreasing is separate from what direction is the magnetic field pointing. And the magnetic field I'm referring to is the magnetic field, the external magnetic field from a magnet, from another coil, from something else, right? It is not the magnetic field of the coil. We haven't gotten there yet. Flux through a coil, magnetic flux through a coil is being caused by some external agent. This is the magnetic field of the external thing. All right. Second step, okay, you apply Lenz's law. Lenz's law, okay? And then the third step is that you apply a right-hand rule to step 2 to find the direction of the current. So let me do this 3-step process so that you understand what I mean by all of these steps. So let's take a look up here at our very first one here, right? Okay. We already identified that the flux is doing what? It's increasing. We're going from 0 to something. But what direction is the magnetic field pointing? In. So my first step here is that this is increasing into the plane of the coil. And I like to write this down because if I don't, I'm going to get lost. Okay? So it's increasing, it's getting bigger, it's going from nothing to something. And the direction of the magnetic field, my X's, are pointing into the screen. I've identified those two things. Step 2, apply Lenz's law. What did Lenz's law say? Fight the change, right? Do whatever you can to fight the change. But the loop cannot start with the word decreasing. When we write down Lenz's law, the only word we can use is increase. In other words, a loop cannot generate anti-field. I said that before. The loop can only make magnetic field of its own. But it will make magnetic field in a direction to fight the change. So how do you fight increasing into if your only word that you can start with is increase? Increase out, right? That's the fight. So that's where you apply Lenz's law, right? In step 2, you must use the word increase. I can't stress that enough. In step 1, it can be increase or decrease. It just depends on what it's doing. But when we apply step 2, when we apply Lenz's law, the coil can only create field. So to fight the change, it's going to increase out. The coil will create magnetic field pointed which way? Outward, right? So it'll come along and it will try to cancel out this change in flux by adding opposite flux that it is generating. Well, now we have the coil generating a field. And the only place that coil can get field from is by having a current flowing in the coil. So what direction is the current flowing in the coil? Which right-hand rule are we going to use to figure out the direction the current is flowing in the coil? It's a hitchhiker because there's no forces here, right? Which hitchhiker is it? Is your thumb the current or are your fingers the current? Your fingers are the current because this is a coil. The current's flowing around the coil. So if the coil's magnetic field, my red dots there, are pointed out of the screen, my thumb is the magnetic field pointed out, What are my fingers doing? They are rotating counterclockwise. Okay. How many conceptual things did you have to hold in your head? A lot, right? This is why I break it down into 3 steps, and I always write down what I'm doing. Because if I don't, invariably I'm going to swap an into or out. I'm going to do something wrong. It's going to be awful. Okay? So make sure that you find a way to keep this straight. You could add more steps in here if you wanted to. Okay? But these are the basic things that I think minimum that need to be identified to be able to apply Lenz's law. So let's do this. Let's do the second one down here on this increase, right? So let's do these 3 steps right here, right? So step number 1. We know this is increasing, but what direction is the increased magnetic flux? It's out, right? So what will be the fight? How will Lenz's law respond? What word must you start with? Increase. Okay? And to fight an increasing out, you're going to increase in. Okay? Now that we've created, the coil has created inward pointing magnetic field, what is the right-hand rule going to tell you about the direction? It's going to be clockwise. Thumb goes into the screen, because that's the direction of the magnetic field. Fingers wrap around in the clockwise direction. How you doing? Doesn't seem so bad, right? We did the easy ones first. This is where your brain's going to start to break. Okay, so let's switch over to the decreasing stuff, right? Okay, so step number 1. We know this is a decreasing case. What direction is the magnetic flux pointed? Inward. Those X's right there are pointing inward, aren't they? Decreasing into. What I want you to do is, in the safety and security of your neighbors next to you, turn to each other and figure out what Lenz's law has to say about this. What is Lenz's law's response to a decreasing into? Go. Okay. Did you come to a consensus? No. What 2 words did you decide on? Say, so you know it has to be increasing, right? It cannot be any other word. On step 2, it has to be increase. So how do you fight a decreasing into? You increase into. What's the magnetic field doing? It's getting weaker, right? So Lenz's law wants to fight that change. It doesn't want the flux to go away. What way is the flux pointing? Inwards. So it's going to make inwards flux to fight the fact that the inward flux is getting weaker. It holds on. No. Like a teenager. Teenagers, I know some of you are, but it's okay, I like you. Teenagers constantly change their minds. Most often to just simply fight what their parents are saying, right? Doesn't matter who's right or wrong. All that matters is if my parents say it, I'm against it. Right? So that's what Lenz's law is. Whatever's happening, it's going to fight it. Notice over here, when the fluxes were increasing, Lenz's law was like, I don't want that flux. Get out of here. I don't want it. I'm going to fight that. But over here, it has flux. It's like, no, what? And what's worse, if you take a magnet and you move it towards the coil, it will fight that, won't it? But now I stop and I pull the magnet out. In stopping, what's the change in flux? It's 0. Loop doesn't care. And now you pull it away. So it goes from an increasing to a decreasing. What's the loop going to do? Fight both ways. It'll fight it going in. It'll fight it getting pulled back out again. I know I lost you. Okay? I know. It's for whatever reason, it's really hard for our brains to latch onto this concept and idea that Lenz's law always does what? It fights the change. What is the change as I bring the magnet towards it? An increase. So it'll push back against that. But as I turn around and pull it out, what is the flux doing now? It's decreasing. So what will the loop do? It'll try to hold on to it. Crazy? Take that up with the guy upstairs, man. This is like, I'm just describing what the universe does. Okay? This is why it's called Lenz's law, right? I'm not proving or deriving anything. I'm just telling you this is what happens. And the reason we're doing all this, the reason we're spending all this time on it is important. This is going to affect us moving into AC circuits and all this beautiful stuff that we know and love today. So hang on for the ride. This is totally worth it. There's going to be some really cool applications of this. No. I know you're on that, but that's not what's happening. Okay. So while we're here, let me explain something else. If I take this coil and I put it on its side and I drop a magnet through, what will the coil do? It'll fight the increase first, but then it gets to the middle where it's nice and even. It's not stops. I'm just dropping this thing through, right? But in the middle, the change in flux is 0. It's like transitioning. The direction of the magnetic field is changing here, right? Okay? But so it's increasing as it falls, and then it decreases on the way out. What is the coil going to do? It's going to fight it. And how's it going to fight it? It's going to make field one way and then switch it to the other way as it comes out. Don't worry, we're going to do that one a lot. Or worry. Let's do our other one over here. Oh, we never did the right-hand rule. So it increases into, right? So it tries to make field of its own, the blue field, right? As this thing goes away. So what do I do with a right-hand rule? Yeah, my thumb goes which way? Into the screen following the blue field. And my fingers wrap around which way? Clockwise. Okay, and then finally, this last case right here. What do we got? It's a decrease out. So now we can only increase, we can only make field. And if the field's going away, pointed out of the screen, the way you counter that is to increase out. The right-hand rule, right? We increase out of the page. My thumb comes out of the page. My hand wraps around in the counterclockwise direction. So thumb comes out of the page, wraps around counterclockwise direction, and I get Counterclockwise. Okay. So what do we know? We know this. Here's how you're gonna, this is what you're gonna practice a lot, okay? To try and nail these directions. I think we've covered the vast majority of possible cases. Now, there's lots of different ways we can draw the pictures. There's lots of different orientations of magnetic field. There's lots of different ways to visualize this. But they all come down to one of 4 situations. What are those 4 situations? Increasing into, increasing out, decreasing into, and decreasing out. Another way to summarize Lenz's law is that an increase into will be fought with a what? An increase out. An increase out will be fought with an increase into. A decrease into will be fought with an increase into, and a decrease out will be fought with an increase out, right? That represents the total sum possibilities for describing how Lenz's law is going to fight things. Yeah. The opposite direction. It goes along with it. It's a good way to summarize, right? But again, you're holding a lot of these pieces of information in your head kind of simultaneously, right? So come up with a method that works for your brain on how to keep track of all of these things. I've suggested like there's 3 steps, right? 3 main phases. There's what the external field is doing, that's step 1. There's what the coil does, and Lenz's law says, and then there's a right-hand rule based on the coil's response. Okay, so let's do some examples of all of this stuff. Okay, oh, let me show you this video because I think this video does help explain kind of like what Lenz's law is doing and how it affects the rate of change of magnetic flux. Yeah, there we go.
Current flows through a coil of wire whenever the magnetic flux through it is changing.
So it's
The current
decreasing,
flows
right?
one way if the flux decreases, and the other way when the flux increases.
Okay.
But the current induced in the wire also creates a flux of its own, whose direction depends on the direction of the current. The flux created by the induced current
Coil
always opposes
external
the
field.
change in the external flux.
External field,
This rule
coil.
is known as Lenz's law. The net result of both fields added together is to slow down the rate at which the magnetic flux through any circuit is able to change.
Did you catch that last part? What does Lenz's law tell us? What happens to coils? Any change in magnetic flux is always slowed down. Whatever's happening with whatever directions are going, the rate of change of magnetic flux through a closed loop of wire will always be slowed down. It doesn't happen instantaneously. So that video, I hope that you saw that there's this external field that's doing something, but then there's a field that the coil is doing. And when you put both of those together, you slow down the rate of change of magnetic flux. Now, let me answer a question that may or may not be occurring to you at this point. Why isn't it like a perfect one-to-one? Why isn't it like perfectly canceling the magnetic flux? Because what? Resistance in the wire. What does resistance do? Resists. It takes energy away from the flow of charges, doesn't it? So what happens is lenses, the current that's established in the coil is always like smaller or lagging slightly behind the external flux change. And so it's always a little bit on the losing side. And so it slows down the rate of change, but it can't perfectly cancel the rate of change unless what happens? Hint, I already showed this to you. What must be true to perfectly match the change in magnetic flux? What does the resistance have to be? Do you remember the superconductor? Do you remember that magnet floating over the top of the superconductor? That was perfect matching of changing magnetic flux. And that magnet was able to just float there because there was no resistance in that superconductor to take energy away. So it could perfectly cancel the magnetic flux of the magnet, oppose it, provide the currents that were necessary to create a magnetic field that kept that magnet floating above the superconductor. That was a bit of a lie because there's a lot more interesting physics going on in there, but we need quantum mechanics before we can talk about that. All right, but it was a good lie.
These two coils of wire are suspended from pendulum arms.
Cool.
The coils are electrically connected through these steel rails so that any current flowing in one coil must also flow through the other.
Nice.
When one of the coils is swung in the magnetic field of a large horseshoe magnet, the other coil also begins to swing between the arms of its own magnet.
What's the frequency, the rate at which those are going back and forth? It's identical.
If one of the magnets is turned around, the second coil swings in the opposite direction as the first coil.
Right? A flux
If a
change
thick
through
wire
one
is
of them
connected
is
between the steel rails,
causing a flux change to the
shorting
other.
out the current,
If we short the current, then nothing's going to happen. It's just going to,
the effect stops.
yeah, nothing happening. Right? But did you see how they were coupled together? And they were coupled together perfectly, weren't they? Right? Okay? It's a really neat effect. All right. Let's do a quiz. Yeah. Should you be doing this by yourself? No. Okay? There's only one time you will be asked to do this by yourself. When is that? On the exam. So, every chance you get before then, practice, practice, practice with other people around you, quizzing each other, asking what's going on, finding out, trying to get to those skills and having that sort of muscle memory about how it works. Okay, let's start putting together Faraday's law of electromagnetic induction, which contains Lenz's law. So where does it contain Lenz's law? I've kind of harped on this before. A lot of resources will write this. I write it like this. Right? But in either case, what are the things that are tipping you off that Lenz's law is a thing? That minus sign right there. That minus sign means fight the change. Whatever this derivative is, we're going to be the opposite of it. Over here, the giveaway are the absolute value signs, right? Just calculate the magnitude and then figure out the directions using Lenz's law. Either way, you got to use Lenz's law. Okay? Don't ever rely on a derivative to tell you what to do. So what I want to do is I want to put this idea together to try to create motion from this idea that there is a fight in the change in magnetic flux, but that we can change. What I want to do is I want to turn this around. all the examples we've done up to this point involved magnetic fields being the thing that causes the change. Well, what if a coil instead changes its voltage or its current? Could that have an effect on an outside magnet? So, the way we can set this up is I'm going to make train tracks. I'm going to have a conductor, not the one that goes and checks the tickets. I'm going to have a conducting wire. I know I said train tracks. Okay? And so I've got a conducting wire, 2 parallel wires that are then connected together just with a resistor. Now, this could be a light bulb. It could be a lot of different things. But the point is, I'm just going to connect a resistor across these 2 train tracks. Because what I want to do is form a closed loop. And then I'm going to lay a metal bar across the train tracks. Now, this metal bar is free to move either way. It can slide along the train tracks or roll along the train tracks. But key to this is the fact that with this metal bar in place, there is a closed loop of conductor, right? Conducting all the way around that loop. And between the train tracks, I'm going to put magnetic field. And we're just going to say where it's pointing into. So this just keeps going, right? The rails keep going infinitely far that way. Okay. The question for us is, what happens when we move the bar? Okay, well, the magnetic field isn't changing. Magnetic field is just a constant into the screen at some strength, right? But more correctly, what changes as we move the bar? It's the F word, but not that one. The flux. Okay? So, how is the flux changing? Okay, so let's say that the train tracks are a distance L apart from each other, right? Whatever that distance is, right? And our task, again, is to figure out how is the flux changing. It could be a little d, it could be a delta, it doesn't matter, right? But the delta can be applied to one of 3 things, can't it? So is the field strength changing? No, I'm not turning up the brightness of the x's. I'm not causing more x's to appear, right? Not causing them to go away. So the magnetic field strength isn't changing. Is the area of the loop changing? Yes. Is the orientation of the loop with respect to the magnetic field changing? No. So we are going to, so is it safe to say I could just call that 1 again? The area is either in or out, and the magnetic field's in, and the dot product's going to be, okay. So what's happening here is I have a B delta A. So now I've got to figure out how my area is changing. Okay, well, let's call this distance x, right? So what would be the area of the loop right now? X times L, right? Just a square, right? Rectangular, whatever, right? So my area, it's a change of x times L, isn't it? But which one of those 2 things is changing? It's just x, isn't it? So I've drilled down here, right? I've got flux. I've got to figure out how it's changing. This is what we were doing before. And I've identified that the change, the thing that's changing is the area, and really the thing that's changing about the area is this one dimension of the area, right? We're like changing its width, if you want to call it that. Okay, so all of this goes back into this statement, right? Oh, by the way, how many turns are there here? 1. So n will become 1. All right, and then this is delta phi b dt. So n becomes 1. This is b times L times delta x, and that all gets divided by delta t. Yeah, I could have left them as d's. I'm being a little bit fast and loose with my d's and my deltas, which is very sloppy of me, but it still works. Okay, so what? Do I know my change in x? No. Do I know my change in time? No. I was given L, V, and X and a resistance for some reason. What's delta X over delta T? It's a velocity. What have we just discovered? We've discovered the voltage that will be induced in this circuit along these wires and through that resistor if we move that rod along at a speed v. So, if that resistor were, say, I don't know, a light bulb, and I grabbed this rod and I jerked it, moved it sideways, what would happen to the light bulb? It would light up, right? There'd be voltage in the light bulb. Would there be current? If you have voltage, EMF, and you have resistance, Ohm's law tells us you're going to have current, right? Light bulb will light up. What happens if I take the bar and I push it the other way? It'll light up. The current will be through the light bulb the other direction, but the light bulb doesn't care, right? Okay. Let's flip that. What happens if I suddenly change the voltage in the circuit? If I move the bar and it causes a voltage in the circuit, I'm flipping the idea. What I'm saying is I'm going to change the voltage in the circuit. So what should happen? The bar would move. So we can find the EMF, the voltage. We know the magnetic field. We know the length of the conductor in that field. Notice X doesn't enter in here, right? It's just the width between the tracks. And I know how fast the bar is moving, I can find my EMF. But if I know the EMF in the coil, I know my magnetic field and I know the distance between the tracks, I can find the velocity that the bar is moving. I can do one or the other. I can generate electricity by moving the bar back and forth, or I can make electricity go back and forth and cause the bar to move. How does this have any practical application? What's an airplane? It's not a metal, well, kind of a metal box. It's a metal bar. This is a top-down view of an airplane. Oh, that doesn't fill me with confidence. Okay, if the airplane is moving this way, and the magnetic field of the Earth, let's say, is directed downwards, it's got to be in the northern hemisphere then. So is this plane moving through a magnetic field with a wingspan L? Yeah. What's going to happen across the wings? motional EMF. Because the plane is moving through the Earth's magnetic field, there will be a voltage across the wingtips. From wingtip to wingtip, there will be a voltage. So let's calculate what that voltage is going to be. For a plane speed, okay, of approximately 900 kilometers per hour, which is roughly 540 miles per hour, which is standard cruising speed at 30,000 feet for most commercial jets. The EMF, given the Earth's magnetic field strength, typical wingspans of a plane, I did some fudging here and some sort of averages, okay? Turns out to be, does anyone want to guess? 2 billion volts? What the voltage is going to be across the wings? 2.7 billion? Just 2? Yeah. You're going to go low? It's half a volt. So are we going to be generating any electricity this way? Just by flying airplanes through the air? No. We are going to be generating a lot of static electricity. Do you guys know that when a plane lands and it pulls up to the gate, that one of the first jobs that must be done in parking the airplane is some poor person has to run up to the airplane with a wire and plug it in? Why? To get all the charge off of it. It does two things. They plug in the wire to get all of the static charge, because as the planes move through the air, it's generated a lot of static charge, okay? And it can be tens of thousands of volts difference between the ground and the plane. So a person with an insulated pair of gloves and an insulated wire and really good boots has to run up, plug it in to drain that charge off, that static charge off, and also provide ground power so the plane can turn off its engines. Because you don't want the engines running while people are loading bags and wasting fuel and all that kind of stuff. All right. So that wasn't terribly interesting, right? Airplanes flying, not going to cause anything interesting to happen. I have here a box. The box just has a switch in it. And more importantly, that box is attached to this coil right here. And I've got a metal bar, which just helps to concentrate the magnetic field in there. It's just an iron bar. Iron responds really well to magnetic fields, so it helps it direct it a little bit more, okay? And what I've done is I have plugged this thing into the mains, directly into the wall socket, okay? So when I flick this switch, I die. No, I will charge this coil. You should be able to hear it. You hear the buzz? Okay. The reason it's buzzing is because there is a frequency at which the wall current is supplied. It's alternating current. And so that means that it goes back and forth. It changes its direction. In the United States, electrical generators produce electrical power at a frequency of 60 hertz. So that means 60 times a second it goes through a full sine or cosine wave, which means that the voltage peaks 120 times a second, right? Starts high at a peak, and then half of a phase later, it's at the opposite peak, right? And then it comes back up. So it's like 120 and then 0 and then negative 120, up and down, up and down. So what you're hearing is the 120 hertz frequency we kind of hear with our ears, or 60 cycle. That's 120. We're hearing the 120 buzz, okay, as this thing shifts its direction back and forth very rapidly, okay? So I've got a coil of wire here that every 1/120th of a second is going this way, let's say, right? So its field is pointed up along this rod. And then all of a sudden, 1/20th of a second later, what does it do? The current flips its direction, so now the magnetic field is pointed down, right? And then 120th of a second later, it flips, and it does this, right? Up and down, up and down, up and down. So this coil is causing a lot of flux change, isn't it? The magnitude of the field is more or less staying the same. It's the direction that is changing very rapidly. All right. What is that? Yeah, it's like a little cylinder or ring or something like that. Okay, it's made out of aluminum. I'm going to put that ring on my launcher. Okay. It's a coil, isn't it? What is the magnetic flux through the coil right now? 0. What's it going to be when I hit that switch? A lot. What is it going to do? Okay. It's one way. What is this? What is this? Okay. I know Halo isn't a thing anymore. But Halo was the first video game to introduce a certain weapon to the zeitgeist, to the popular culture. The railgun. Okay, what was a railgun? It was a device that shot a mass, but no gunpowder was required. It was all electric fields. This is a railgun. I just gave you the physics for a railgun. Yes. Now, I'm a pacifist, but I still think this is cool. All right. What is this? It's a smaller ring. Okay? Less mass. So it's half the height, right? So half the mass, right? So what's your prediction for what it's going to do? It's going to go through the roof? It's a brand new building. I haven't done this yet, right? Yeah, no, there's always got to be damage somehow. You ready? So your prediction is it's going to go higher? All right, here we go. Why didn't it go as high? Less coils, right? Less effective number of turns, right? Half the number of turns. So it only really went half the height, didn't it? So it only goes up like roughly there. Right? Okay. All right. So what about this one? This one, help me out here, Olaf. Which one's heavier? Okay, the copper one, right? Okay, much heavier. So, but they are the same dimensions, right? Same height, same effective number of turns. So what's going to happen here? It's not going to go as high. So there, the change in flux is the same, number of turns were the same, but this is more massive, right? We're no longer talking about motional EMF. We're talking about Newton's second law, right? It has a bigger mass. So the same amount of force will accelerate it less, right? All right, let's put this one back on again. You guys ready? What is this? It's not a loop, right? So there can't be any induced EMF. Why not? It's a loop. All right. Okay. So what I've got here, I've got a light bulb, like that one that we saw in the video, okay? But this light bulb is attached to a coil, right? Right now, the light bulb's not lining up, right? Because there's no change in magnetic flux through the loop. But if I put this over here and turn it on, do you see how it lights up? Okay? Notice, no connection. Pretty amazing, wasn't it? What did I just demonstrate? Wireless electrical transmission. Why is this not a thing? It is a thing. What do a lot of our phones now do when we put them on their stands and lock in? They will charge wirelessly? No, there's a ton of wires in here. But there's no plugs, right? There's no plugs. How is it that your toothbrush or your phone is able to charge wirelessly? Faraday's law of electromagnetic induction. And whatever your phone's charger is doing, what is the coil in your phone doing now that you know about Lenz's law? It's doing the opposite. But the power transfer is the same. Energy must be conserved. We are so far from done right now on the cool things I can show you that Faraday's law and Lenz's law causes to happen. On Monday, Faraday's law lab. You're going to come in, we're going to play with Faraday's law, you're going to do some measurements of it. Tuesday, we're going to continue with the implications of everything I've just shown you. Have a great weekend if I don't see you in Grasp.
If you add both the aluminum coils, the smaller one and the bigger one, will it affect how high it flies as well, or is it the same?
Which one do you want on the bottom and which one do you want on the top?
Small on the bottom, big on the top. Oh, it does affect it.
The arc reactor? Iron Man never said.
In the movie, didn't it had a magnet because all of like the shrapnel and the stars.
Well, the arc reactor was supposed to power the electromagnet that was keeping the shards from entering his heart. But he never really said how he managed to get 2 car batteries to ignite an arc reactor. Like the physics there doesn't work. Don't ask too many questions. It'll ruin Marvel for you. Sorry.
I saw a person was flying like power plant, like
A bazooka, nothing else.
yeah.